Hello. Okay, so in this video, we're going to discuss different ways to model different types of scatter plots, as well as just the difference between linear models, quadratic models, and exponential models. Okay, so here are some examples, as you can see over here, of linear, quadratic, and exponential scatter plots. So we have dealt with lines in the past, right? So this, as you can see, this has a shape of a line. This quadratic model, quadratic models are basically the shape of a parabola. We've done that before. We're going to go into exponential models very soon, but we've done that in some shape or form when we've had to find the domain and range of something of this shape. Okay, but that's generally the kind of shapes that we're looking for. Okay, so a linear model creates a straight line. Quadratic creates a parabola. This is a parabola. And exponential basically rises or falls quickly in one direction. As you can see, this would be an example of falling quickly in one direction. Okay. Let's go ahead and look at this particular example here. So one, determine whether each scatter plot shown below would represent a linear, quadratic, or exponential function. Okay, well, what I see here is if I were kind of just draw the shape. So if I just kind of just draw this shape here, it looks like this is going to fit the shape of a parabola. So if it's the shape of a parabola, this would represent a quadratic function. So recall like quadratic formula, quadratic function, like something of the form ax squared plus bx plus c, right? So that would be a quadratic model. This one here, it looks like it's rising quickly in one direction. So, you know, if I made this go more up, as you can kind of see, this shape here would represent an exponential model. Okay, so this is going to be exponential. Okay, this one here, this looks like it takes the shape of a line. Okay, cool, bad line. So as you can see here, so that kind of takes the shape of a line. So in this case, this would represent a linear function. Okay? So that's basically how that would work. Okay. Let's go ahead and look at a few more examples. Let's say instead of like the scatter plot, let's say you have a table of values instead. Okay? So when considering these tables, you want to look for a specific pattern. Okay, so for a linear function here, it says you never see the same y value twice. So as you can see, you can't see the same y value twice. And the first difference is the same. Okay, so what that means by the first difference is basically the difference between these two numbers here, these two numbers here, and these two numbers here. Okay, so for example, what I see is, well, the difference between -1 and 1 is going to be, you'd add 2, right? Between 1 and 3, you'd have to add 2. Between 3 and 5, you'd have to add 2. Okay? For a quadratic model, it says you can see the same y value more than once, so something of this nature right here. And the second difference is always the same. So this, okay, I forgot about this. So this represents the first difference. Okay? So first difference. Okay? So let's try to find the first difference between each of these numbers. So what we have, well, between 1 and 0, well, we just be subtracting 1. Here we'd be adding 1. We'd be adding 3 here. And then we would be adding 5. And then between these numbers, so this is our first difference. Okay, this kind of now looks like, as you can see here, so you see this, kind of looks like this now. Okay, so if we find a second difference between these, well, between -1 and +1, that's going to be +2. This is going to be +2, and this is going to be +2. So this represents our second difference. Okay. For an exponential function, what we're looking for is a common multiplication pattern in the y values. So you can see here, as if you go 2, 4, 8, 16, 32, well, I see that's common multiples of 2. And you never see the same y value twice. So in here, I don't see any y value that's repeated, kind of like what we have here and here. So generally, what we have is we can go ahead and just think about it. So, well, 2 times 2 is 4, right? 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is going to be 32. So that's our common multiplication pattern, if that makes sense. Okay. So next part on the bottom here. So it says, does the table of values represent a linear, quadratic, or exponential function? Okay. So generally what we're doing is we're trying to look for a pattern between the table. So what I see here, if I look at it, well, if I try to compare the numbers, well, I know 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. This looks like it's going to be multiplying by 3. Okay. So since we're doing a multiplication pattern, this represents an exponential function. Okay, so it's going to be exponential. Okay. This one here, what I see is it looks like a pattern of subtracting 4, it looks like. So if I subtract 4, subtract 4, subtract 4, subtract 4. So this means this would represent the first difference, right? So this is the first difference, kind of like what we have here. All of these numbers are all the same. So this, in this case, this would represent a linear function. If you were to plot these points, it's going to represent a linear function. And that's another way you could do this. You could use decimals if you want and just plot all these values and see what it looks like. Okay. Then this one here. So what I see here is, well, this, you can see the same y value more than once, right? So since you can see the same y value more than once, so for example, this one you would subtract 12. This one you would subtract 4. This one you would add 4. And this one you would add 12. Okay? And that would represent our first difference. Okay? First difference. If you wanted to figure out a second difference, well, you can figure out the difference between negative 12 and 4. Well, you would add 8. This one you would add 8. And this one you would add 8. Okay? So what we have here, this represents our second difference. Okay? So second difference is going to be the same. Okay? So in other words, what we have here, we have a quadratic function. Okay? So that's generally what we're doing. Okay? And that's basically it for trying to find the difference between linear, exponential, and quadratic functions. Okay? In the next part of this video, I'm going to describe the difference between exponential growth and decay. So we're finally going to go a little bit more depth into what exponential functions are. Okay? But first I wanted to just illustrate this difference between each of the three before I went and talked about exponential functions. Okay? I'll see you next video. Bye. Hello. Okay, so the purpose of this video is to basically describe the difference between exponential growth and exponential decay. All right, so what we have here, so this is an example of the parent function of an exponential function. So basically what we have is it's going to be some constant raised to a power. That's basically how to describe an exponential function. Okay, so in this case here, if this constant is greater than 1, this says that this function is going to be an exponential growth. So exponential growth. And the function itself is going to be increasing. Okay. If this number is between 0 and 1, okay, it's going to be this thing called an exponential decay. Okay, so an exponential decay. And it's going to be the opposite. It's going to be decreasing. Okay. There's also some terminology about an asymptote. So an asymptote is basically a line where the graph gets close to, but it never crosses. Okay. We're going to go ahead and look at this example. We're going to apply some of these things, these definitions up here, just to help you guys out. Okay. So let's say we plot a bunch of x values. Let's say we take like -2, -1, 0, 1 and 2 or something. Okay? If we plug x into here, this is 2 raised to the negative 2. Okay? Recall that, remember in unit 0, if you have a negative exponent, this is the same thing as 1 over 2 raised to the second power. And 2 raised to the second power is going to be 4. So this is 1 over 4. Okay? If we plug 1 into negative 1, this is 2 raised to the negative 1. So what we have is this is going to be 1 divided by 2 raised to the first power. And 2 raised to the first power is going to be 2. So this is 1 over 2. Okay, we plug 0. Okay, 2 raised to the 0 power. Remember, anything raised to the 0 power is going to be 1. Okay, if we go ahead and plug 1, 2 raised to the first power, that's 2. 2 raised to the second power, and this is 4. Okay, let's go ahead and plot these values. Okay, so we have negative 2, and 1/4 is about 0.25. So if I just show you right here, this is negative 2 comma 1/4, and then we have negative 1 comma 1/2, so that's going to be the next one, so that's going to be negative 1 comma 1/2. Then we have 0 comma 1, it's going to be right there, and then 1 comma 2 is going to be up here, and 2 comma 4 is going to look like this. Okay, so generally what we're creating this exponential function, so it's going to look something like this. So it's going to just come up, and that's the general shape of what this looks like. Okay, so if we look at this here, this kind of goes back to what I was telling you about increasing or decreasing slope. You know, like as you can see here, this function is increasing. The slope is generally becoming more and more positive. Okay, so this would represent an example where the function is increasing. Okay, linear or non-linear. Well, remember, linear, it has to be a line, right? So this is obviously non-linear. Okay, non-linear. Okay, the domain of this, we're looking at the x values. So as you can see here, this function continues this way in the x direction, and it continues this way as well. There's no restrictions on the x's. So since there's no restrictions on the x's, basically the domain is going to be from negative infinity to positive infinity. Okay, now let's look at the range. In order to determine the range here, so now we're looking at the y values instead of the x's. Domain, we're looking at x's, range, we're looking at y's, right? So in order, if we're considering the y values, as you can see here, this, it looks like if you were to graph this, it's going to keep going this way. It's going to approach 0, the y value of 0, but it doesn't cross it. It doesn't go beyond this. It's just going to stop there. Okay? So basically what that says is the y values are just going to exist in that region, if that makes sense. So if I were to just kind of shade that for you, that you can see right here, that's generally what's happening. Okay, so in other words, the range is going to be y values that are greater than 0. Or in other words, you could also write it, like this if you wanted to. That's another way that you could write it. Okay. Y-intercept. Okay, so the y-intercept, as you can see here, this is where it crosses the y-axis. So it's going to be at 0, 1. Okay. The asymptote. So the asymptote, this is what I was trying to mention earlier. So the graph doesn't go beyond this border. So think of it as the police trying to protect all the protesters from getting into Capitol Hill, right? So this is going to be the line y equals 0. So this refers to this asymptote, a line which the graph gets close to, but it never crosses. Okay, and is this exponential growth or decay? So as you can see here, the function is increasing. So this is going to represent exponential growth. So this exponential growth, right? So that's generally how that first one works. Okay, let's go ahead and look at another example. So down here, all right. So let's say I give you this here. Okay, so let's go ahead and take this. So we have -2, -1, 0, 1, 2. Okay, so same idea. What we're doing is we have 1/2 raised to the -2. I'm going to help you guys out a little bit. We're just going to convert that 1/2 into a decimal just to make things a little bit easier. So this is basically 0.5 raised to the -2. So this is the same thing as 1 divided by 0.5 squared. Okay, so 0.5 squared, if I do that, 0.5 squared is going to be 0.25. Okay, and 1 divided by 0.25, if you do the math for that, that is basically going to be 4. Okay, then if we do this one, if we have 0.5 raised to the -1, so this one is going to be 1 divided by 0.5, or a raised to the first power, right? Because with this here. So if we raise that to the first power, well, 0.5 is just going to, 0.5 raised to the first power is just 0.5. So what we have is, well, 1 divided by 0.5 is going to be 2 if you put that in the calculator. So this is 2. Okay. Anything raised to the 0 power is 1. If I do this, if I raise to the first power, this is 0.5. And then this one as well. So if you wanted to, yeah, if you want to leave it as a 1/2 raised to the second power, you can. And that's 1/4. Or if you wanted to, just like I showed you earlier, basically you have 0.5 squared, and that's 0.25. Okay, so you can treat everything as fractions or decimals, whatever makes it easier for you. Okay, but anyway, let's go ahead and graph this. So -2, 4 is going to be up here. Okay, so this is going to be, I'll just show you. This is going to be -2, 4. And then this is going to be -1, 2, 0, 1. And then 1, 0.5, 2, 0.25. Okay, so what we're going to do is we're just going to connect the dots. So you can see here, we can just connect the dots that you see right here. I should draw a little bit better graph. Okay. So as you can see here, this is going to be the opposite. Okay, so what we have here, this represents the function that is decreasing, right? So this on top was increasing. This is going to be the opposite. This represents decrease. Okay, so this is decreasing. Linear or non-linear? Well, still, again, like I said, straight line is going to be linear. This is not a straight line. So this is going to be non-linear. Oh, not right today. Okay, the domain, as you can see here, we're looking at the x values that exist, right? So as you can see, it doesn't look like that the x's are restricted out. It keeps going up this way, and it keeps going this way. So the domain for this is going to go from -infinity to +infinity. We have the range. So the range, this it goes off what I showed you earlier, right? So this graph doesn't go beyond here. It stops at that point. So it's going to be everything that's above that you see right there. So the range is going to be y values that are greater than 0. Y-intercept is where it crosses the y-axis, 0, 1. Asymptote is going to be the same as the other one as well. So you can kind of see, I'll draw that a little bit better. So as you can see here, this basically says the graph is not going to cross that line. So you see this asymptote is the line y equals 0. Okay, so this is going to be y equals 0. And then, as you can see here, kind of what I showed earlier with the example, right? So if I come up here, so it says if you see that this is decreasing, this would represent exponential decay, right? So we're going to use that same idea here. So since this function is decreasing, this is going to represent exponential decay, right? Okay, so that's basically it for this type of example, right? All right. Okay, so let's go ahead and summarize what we went over. So recall earlier, so we said the parent function for an exponential function is going to be something like this. So b raised to some power. So this says, well, if b is greater than 1, this is exponential growth. And if the number is between 0 and 1, this represents exponential decay. All right? So basically what we're doing here, so if we have y equals 5 raised to the x, well, we're just looking at this number here. Okay? So what I see here is, well, 5, this is 5, right? So 5 is going to be greater than 1. So this represents exponential growth. Okay? This one here, so 0.6 is between 0 and 1. So this is going to, so if I were to write this, this represents exponential decay. Okay? This one, 1.2, well, if I put 1.2 into here, well, 1.2 is greater than 1. Since 1.2 is greater than 1, this is going to represent exponential growth. Okay? 12 over 5. So if I put 12 over 5 in here, well, that's, if I divide that, that's like 2.4. 2.4 is greater than 1. So if I were to just do that, so I could either put like, yeah, 12 fifths is greater than 1, or I just 2.4 is greater than 1, same thing. This is going to be exponential growth. Okay. This one, 0.98. Okay, 0.98, that is between 0 and 1. Okay, so what we have here, so if I were to write that, as you can see, this represents exponential decay. All right, this one, 0.2. 0.2 is between 0 and 1. So, same idea. This is going to represent exponential decay. Okay. 1.04. So 1.04 in this case is greater than 1. So this is going to represent, so I'll just write this here. This is representing exponential growth. Okay. And the last one, 3/4. Well, 3/4 falls between 0 and 1. Okay, so since that falls between 0 and 1, so I could write it, like 0.75, 3/4 is 0.75. This represents exponential decay. Okay, so that's generally how this works. Okay, so yeah, if I went back to, you see this, what I showed you earlier here, this is why, well, if this number here is greater than 1, as you can see, this represents exponential growth. If this 1/2 or 1/2 is 0.5, it's between 0 and 1, it's going to show something decreasing. That is represented by exponential decay. All right? Let me know if you have any questions on anything that I have shown you. Okay? And I'll see you later. Bye.